Hello and welcome to this challenging bond enthalpy example. Let's have a quick look at it and decide first of all why it's a bit more applied. Usually a bond enthalpy calculation will ask you to use bond enthalpy data to work out the value of delta H. In this case, you're given the value of delta H up here. So they want you to work out the actual bond enthalpy, the average, bond enthalpy for the S double bond O bond. You assume that sulfur dioxide and sulfur trioxide contain only S double bond O bonds. So this allows us to visualize what's actually happening by writing out the displayed formulae of our reactants and our products. So using the equation that we normally use to work out delta RH using bond enthalpy data, we can put in delta RH as minus 192. We can incorporate 498 kilojoules per mole into the bond enthalpy of reactants, and then we can assign X, our unknown, as the S double bond O, because it turns up virtually everywhere else. So you can see there's 4 of them on the left hand side, and 1, 2, 3, 4, 5, 6 and on the right hand side in the products. So that allows us to write this expression out. So collecting like terms to solve for X, you get minus 2X equals minus 690. So X, our S double bond O bond enthalpy, will be plus 345. So a bond enthalpy is based on bond breaking, so therefore it's an endothermic process, hence a positive value will come out of your calculator as opposed to a negative one. So looking at the next one, it then says the actual bond enthalpy for the S double bond O bond in SO2. So remember the first part was talking about average bond enthalpy spread over those two molecules, SO2 and SO3. This time they tell you that the S double bond O bond in SO2 is 531, so there's 4 of them. So this changes the math slightly. So using the same expression, this time I'm going to call the unknown bond enthalpy, the S double bond O bond in SO3, I'm going to call that Y. So 4 531s plus 1 498 minus 6Y will give us minus 192. So again, bond enthalpy of reactants is in the square brackets, bond enthalpy of products is 6Y. So obviously all of this in the square brackets adds up to 2,622. Subtract 6Y, it gives you minus 192. So it's quite straightforward to solve for Y and end up with 469 kilojoules per mole to the minus 1. Okay, I hope this has been a useful look at a slightly more difficult example. Thanks for listening. Until next time, see you soon.